Hey everybody. So in the last one, we developed a way to take derivatives of inverse functions, and I have the formula here, right? There's some details we need to make sure that function, the derivative of f, well, first of all, that f is invertible and differentiable, and that the derivative of f at this point, f inverse of x, is not zero, right? But here's our basic formula. We're going to use this to develop a couple of other derivative rules, and we're going to start by developing the following. We want to show that, let's keep this separate. We want to show that the power rule works right? So we started out by showing this works for positive whole number, positive integer exponents, and then we eventually extended that to the negative integers. But I want to show now that it works for rational exponents, right, where n is the quotient of two integers, right? That's not quite all the numbers, right? There's a whole, the rational numbers don't make up all the real numbers. In fact, there's more in some sense of the other things that aren't rational, all the irrational numbers. But we're not quite there yet. So far we'll get it for the rational numbers. So we're going to start. Let's start first by showing it when we have not quite a rational number. Well, it is a rational number, but a particular one over some integer. Okay. So this, let's let g of x be x to the 1 over n, which is the inverse of f of x equals x to the n. Okay, so now we're going to use our inverse function theorem, right? We know then that g prime of x is equal to 1 over f prime of g of x. Right, so this is just this theorem here, right? So in the inverse function theorem, we have f inverse and f. I'm just calling it g. It kind of makes it a little easier to follow, I think. But this g is just f inverse, right? I just stated that in words. So I'm just putting g of x where we see f inverse in here, so that it has a more distinct name to make the notation a little easier to follow. Okay. So by the power rule, we have that f prime of x is n x to the n minus 1, right? Because we were starting out with n being an integer. And we already know this is true for the integers, okay? So then f prime of g of x is going to be n. So I'm putting in g of x, x to the 1 over n, for the x, right? And then I still have this n minus 1 power there. Okay, so now let's work on this just a little bit. This is going to look like n x to the n minus 1 over n, or actually let's leave it like this for now. So then g prime of x is just 1 over this whole thing, n x to the n minus 1 over n. Okay, that's an exponent. It's getting a little crowded there. All right, so I can rewrite this as 1 over n times 1 over x to the n minus 1 over n. And then using the rules of exponents, I can just make this negative and take this into the numerator. And then I can distribute that negative to get x to the 1 minus n over n. And then I can rewrite this fraction in the exponent. 1 minus n over n is simply 1 over n minus 1. And so there is the power rule with this 1 over n. We took the, right, we started with, let's just state it very clearly here. We started with x to the 1 over n. We're taking the derivative of that. That's what g prime is. Skipping all these steps in the middle, we arrive at, we take that 1 over n power down front, that's what we have here, and we subtract 1 from the exponent. So for instance, we now can say, if I was to take the derivative of x to the 1/2, I get 1/2 x, and then I subtract 1 from 1/2 to get negative 1/2. Okay, so we've now extended this power rule to some of the rational numbers, the ones with 1 in the numerator. So let's see if we can push this a little further. So now let's take the derivative of x to a rational number, right? M and n as a quotient for our exponent. Sorry, the sun just peeked out and is shining in my eyes. So we've got, I'm going to rewrite this just using the powers of exponents. Okay, so remember, m and n are both integers here. So now I've got the derivative of, I've got the mth power function, and then I'm putting the 1 to the nth power function inside of it, right? We have a chain rule here. This is a chain rule where our outer function is to the m power and the inner function is to the 1 over n power, right? Well, we know how to take derivatives of the chain rule. I'll take the derivative of the outer function. That exponent comes down. And I get m minus 1. And then I now know how to take the derivative of this 1 over n. That's what we did up above. So we get times the derivative of the inside, 1 over n, x to the 1 over n minus 1. Okay. All right, let's do some simplification here, okay? So let me get a little more space. All right, we've actually got everything we need. So let's just do this algebra off to the side here. There's just a few things we have to do. I'm going to do it down here, and then we'll put the results up here. So we've got m x to the 1 over n, m minus 1 times 1 over n x. And I'm going to rewrite this exponent as it was before I turned it into 1 over n minus n. I can rewrite this as 1 minus n over n. Okay. So now let's just do some algebra. I know I can move, we've got a big multiplication problem here. So I'm going to take all the constants to the front. I've got m and I've got 1 over n. So this is going to be m over n. And then I'm going to take this x to the 1 over n to the m minus 1, use the properties of exponents. I can multiply those two exponents. So this becomes m minus 1 over n. And then I've got that times x to the 1 minus n 1 minus n over n. Okay. All right, so we're almost there. Now let's combine. We know, using the rules of exponents again, that we can combine these exponents by adding them. So m minus 1 over n plus 1 minus n over n. What is this going to give me? Well, here, let's do a little work outside of this. Let's just look at that exponent, m minus 1 over n plus 1 minus n over n is equal to m minus 1 plus 1 minus n all over n. All right, so we have a common denominator. So I've got a minus 1 and a plus 1. Those disappear. I've got m minus n over n, which I can rewrite as m over n minus 1. So this whole thing becomes m over n x to the m over n minus 1. And that's our result. M over n x to the m over n minus 1. Right? And that's exactly what we wanted to show. This is, again, let's just summarize here. We have d dx of x to the m over n. Skipping all that work in the middle, we take the exponent down front, and then we subtract 1 from the exponent. And there we have our power rule now extended to all of the rational numbers, okay? And I've expressed in the beginning, we are eventually able to use it for all real numbers, and so we're free to do that at this point. I haven't proved it yet, but we'll show that at some point. But it's nice to know that where this comes from. This is a good use of this inverse function theorem that we can get these. There's other ways to make this, to get this result, but this is a pretty good one. Let's do a couple of examples. Let's just go to a new page. So for instance, if I want to now take the derivative of something like x to the 5/3, I get 5/3 x to the 5/3 minus 1, or 5/3 x to the 2/3, right? Let's also see what happens when we use this in combination. We now have things like, let's say we have y equals the square root of 3x. Let's do 3x squared minus 9. Okay, so we can rewrite this as that quantity to the 1/2 power, and then we can take the derivative, right? 3x squared minus 9 to the 1/2. And here we have a chain rule again. So let's just remind ourselves of the chain rule. If we have the function f of x equals x to the 1/2, and g of x is equal to 3x squared minus 9, then this function y is equal to f of g of x. Right? That's what y would be. We're just putting this 3x squared minus 9 into the square root. Well, we know the derivative of that, y prime, is f prime g of x times g prime of x. We've got f and g here. F prime, we know we did this one up above using our new rule, 1/2 x to the negative 1/2. And then g prime of x is going to be 6x. Oops, I forgot my equal sign. It's going to be 6x, right? So this is going to be, right, just what we have up here, f prime g of x, g prime of x. So f prime is 1/2 x to the negative 1/2, except I'm not putting x into it. I'm putting g of x into it, which is 3x squared minus 9. And then we're multiplying that all by g prime of x, which is 6x. We can do a little bit of simplification here. So I've got a 6 and a 1/2 are being multiplied. So we'll have 3, and I've got an x, and I've got 3x squared minus 9 to the negative 1/2. This is perfectly correct. You can also write this as 3x if you like radicals and fractions. I don't, but maybe this is a more familiar way to see this for some of us. There's an expression for the derivative of this function. So great, this is a nice extension of our rule and a good use of the inverse function theorem. Okay, that's it for this one. In the next video, we'll do inverse trig functions. These are another big step forward for us, adding a new tool in our toolbox for derivatives. Okay, thanks everybody. I will see you next time.